Okay, this video is going to talk through what's called linked lists. It's going to talk through how they are implemented and how we traverse them. To traverse means to travel through, to output, basically how an algorithm will trace through that structure. So a linked list is a dynamic data structure. Dynamic means that the size of the structure can vary at runtime. So while the program is executing, the size of the structure can change. This is different to a static structure. A static data structure is something like an array, where a static data structure, once we set the size, that is the size how it remains. And this means with a static data structure we can end up with wasted memory, because if you set the array as size 50 but you only ever use 4 spaces of the array, then you have 46 spaces unused. A dynamic data structure, as we say, is a structure where the size can vary at runtime. Each item in the list is called a node, and this contains an information field, which is the data, and it also contains the next address field, which is known as a pointer. So the pointer gives you the position of the next node. So the link field in the last item indicates in some way that there are no further items. We usually use 0 to denote the end of a list. As I said, a pointer, this is a variable that contains an address or a location of a memory location. What we never say a pointer points, because all a pointer is a variable, and this just holds a number, and that number refers to the next memory location. A null pointer, as we mentioned previously, this is used at the end of the list to indicate that there are no more values in that list, and this is either represented by a 0 or a 1. So a linked list then really looks like this if we're going to look at it conceptually. So if we're going to look at it from a viewpoint, we have a variable that holds start, known as the start pointer. It's just a variable that has a number which indicates the first item in the linked list, and this is a node. So each node contains a data part and a pointer part. Data, pointer, data, and their last node has a null pointer. The idea of a linked list is to have a fast access to data via the pointer systems. So a linked list must have a starter pointer, and this holds the address of the head of the list, so the first item in the list. The last node has the null pointer. Here we've got a linked list that's been set up, and this linked list has just 3 items in there, animals, and a linked list is to set up those animals in order. This is node 1, this is node 2, this is node 3. So the start pointer is giving us a value 1, which is saying we're going to start at node 1, which is cat. Cat's pointer indicates that we then move to node 2, which is dog. Dog's pointer indicates we move to node 3, which is pig, and pig's indicates there's no more to go to. Now if this was slightly different, let's say that this was a zebra, for instance, then all of our pointers would change. If we want, the purpose of our linked list is to keep things in order, in some kind of order, maybe numerical, maybe alphabetic. So our start pointer in this case would be 2. And without getting too complicated with arrows, I'm just going to maybe leave the arrows as they are at the moment, just indicating that from 2 we're going to dog, dog we're going to pig, pig we're actually going to go to zebra, and zebra will be a null pointer. Let's say just ignore if we might want to actually move these boxes around. We can look at it conceptually then. and then we've got a linked list set up. This shows that actually stored within that linked list, the items don't need to be in order, they can be in any order. It's the pointers that actually allow us to travel through, to traverse that list in order. Our start pointer says start node 2, dog, pig, zebra, end. So therefore it's very useful and very powerful. Now the data structures, like a linked list, they can be set up using arrays. So I'm going to have a look here a moment. We could have our position. We could have our data and have our pointer. So we could have, if I'm going to create this as a static structure, so I've got two arrays there, and we're not going to use position 0 because we're going to use that as a null pointer, but you can imagine we might have, here are the 5 positions. So if we put some data into these linked lists, for instance, let's have food items. We'll have egg, bacon, sausage, and mushroom. Okay, and we'll have a start pointer. So the start, if we're going to put these in alphabetical order, start pointer will point to number 2. This will give the address position number 2 where we start. Bacon, the next one to come along is egg, so bacon's pointer would be number 1. Egg would then point to mushroom, mushroom would point to sausage, and sausage would be a null pointer. And that is our linked list set up, how it would look like stored in arrays. Well, we see that's a bit more easy to understand how the computer orders that when we look at it in this view rather than the conceptual view. Now if we had something else come along such as orange juice, then we'd have to follow it through. Bacon, egg, mushroom, this would change to 5, and orange juice would then change to 3, to sausage. So that is a view of what the linked list is, how that is set up. Now the linked list is very useful because it makes inserting and deleting elements much quicker. Imagine compared to a linear list, if we deleted one element, would have to move every other element down one to give us that free space. If we wanted to add something into an ordered array, we'd either need to do a bubble sort, some kind of sorting algorithm on it, or compare each item within that array and insert it in the right place. With a linked list, we just add it to the end. So it makes insert and delete elements much quicker. It's just the pointer fields that are changed. To insert a value at the beginning of the list, just the start pointer must be altered. Let's go back to our example. Let's say we've increased these to 6 positions now, and let's say we wanted to add an apple for breakfast as well. We'll have an apple. Then the apple will be the start point now, alphabetically. So actually that new item takes the start pointer as its pointer, and the start pointer then becomes 6. So we go 6, 2, egg, mushroom, orange juice, sausage. Going to our first example, there's the linked list. If a baboon came along, it looks something like that. The start would indicate we're going to the baboon first, then to cat, then to dog, then to the pig. If an elephant was added, Can you see where the elephant would go? That's right, the elephant would go there. Looking at it in the table point of view, table is often much easier to see, much easier to understand, especially in programming terms. So here we've got another example. This is a list of people's surnames, and the start pointer number 1 indicating Browning. So Browning then goes to Cray, who goes to Johnson, who goes to Turner, and then it's the end of the list. Notice something extra that we've added to this is a next free pointer to indicate the next available item. This is useful when we start to implement the code for a linked list. The next free pointer, number 5, gives us where we put that next item. So let's add somebody. Let's add Mortimer. I'd just like you to pause the video yourself and try and draft out what all the changes would be if Mortimer was added to this linked list. Now, was you right? We would start at 1, Browning. Browning would go to Cray. Cray would go to Johnson. Johnson, instead of going to Turner, would now go to the new value, Mortimer, and Mortimer would then go to Turner. Then we would end. Here's something different. What if we deleted somebody? Let's delete Johnson. Who indicates that we've moved to Johnson in the first place? That's Cray. So Cray needs to bypass Johnson. Again, try and draw this out and have a look to see if you can see which values change. Pause the video now. Was you right? So let's have a look. What we haven't actually done is we haven't physically removed Johnson. We've just changed the pointers. So we start 1, Browning, go to Cray. Instead of Cray going to Johnson next, Cray now goes to Mortimer. Mortimer then goes to Turner, and we end. And so the pointers skip out Johnson. That is the way that the deleting works. So the item is still there in memory, in the storage, but it's just bypassed. This makes the deleting much easier. One of the things we could do is have a second set of pointers which then operate the next 3. Because one of the problems that we're going to end up with here is if we suddenly get a 6th item, then there's no more free spots. And if we've got something in these, even though they're not used, imagine if we delete Browning, we delete Turner, we delete Mortimer, so we've just got Cray left, then this full linked list is taken up and becomes unusable. But that, in essence, is what a linked list is and how that works.